Hey everyone, in this video we're going to work through implicit differentiation step by step. This topic is different from the derivative problems you may be used to, because in these equations we have y and x on the same side. So y is not isolated by itself, instead x and y are mixed together in the same equation. So the main goal here is not just taking derivatives, it's learning how to differentiate both sides carefully, keep track of where y appears, and then solve for dy dx. The big rule to remember for this entire video is whenever you differentiate a y term with respect to x, you need to multiply by dy dx. That's the key idea behind implicit differentiation. Let's go problem by problem, and we'll go more in depth about what that really means. So, this first problem is x squared plus y squared equals 49. So this is a classic circle question. Since y is not isolated, we differentiate both sides with respect to x. The derivative of x squared is 2x dx over dx, but dx over dx just cancels out. The derivative of y squared is 2y dy dx. Why? Because y is really a function of x, so we use the chain rule, and the derivative of 49 is 0. So we get 2x plus 2y dy dx equals 0. Now let's solve for dy dx. Move 2x to the other side, and now we divide by 2y. And then so the derivative is negative x over y. Very standard first example. Okay. So we're going to find the derivative of x cubed plus y cubed equals 9. So same idea, but now with cubes. So we're going to have the derivative of x cubed, which just gives 3x squared. And then the derivative of y cubed gives 3y squared dy dx, and the derivative of 9 is 0. And now we solve for dy dx, so we subtract 3x squared to both sides. And then we divide by 3y squared. So our final answer is negative x squared over y squared. Again, the only new thing is remembering that the derivative of y cubed is not just 3y squared, it's 3y squared dy dx. So, let's move on to the next question. So we're going to find the derivative of xy equals 12. So now we have x times y, so we need the product rule. Differentiate both sides. So once we use the product rule, we get x dy dx plus y equals 0. And then you could also write it as, it's already written as that. Okay. We solve for dy dx. So we subtract by y. And we divide by x. So then the derivative is just negative y over x. This is a good reminder that implicit differentiation often uses regular derivative rules as well. Let's move on to the next question. So we're going to have sine xy equals x. So now we combine implicit differentiation with the chain rule. Let's differentiate both sides. The derivative of sine u is cosine u times the derivative of whatever is inside. So we have cosine xy times the derivative of xy equals 1. Now we differentiate xy using the product rule. So we get x times dy dx plus y. And now we put it all together, and then we have cosine xy times x dy dx plus y equals 1. Now let's solve for dy dx. First, divide both sides by cosine xy. And then we know that 1 over cosine xy would just become secant xy. And then so we can subtract by y. And then we can divide by x after. So the final answer is secant xy minus y all over x. This is a really nice example because it uses both the chain rule and the product rule together. So this next question is e to the power of xy equals x plus y. This is another chain rule problem. So we differentiate both sides. The derivative of e to the power of u is e to the power of u times the derivative of u. So we get e to the power of xy times the derivative of xy equals 1 plus dy dx. Now we solve for dy dx, and as you can see, there's a dy dx on both sides. So we can expand first. So we get x to the power of xe to the power of xy times dy dx plus ye to the power of xy equals 1 plus dy dx. Now we move all the dy dx terms onto one side. So we get xe to the power of xy times dy dx minus dy dx equals 1 minus ye to the power of xy. And we can factor out dy dx. Minus 1 equals 1 minus ye to the power of xy. And then we can just divide whatever's in the parentheses. And so the final derivative is 1 minus ye to the power of xy all over xe to the power of xy minus 1. So this one looks more complicated, but the process is still the same. We're going to differentiate carefully and then just solve for dy dx. Let's move on to the next question. So we're going to have x squared y plus y cubed equals 7. So here we have a product in the power of y. So we're going to differentiate both sides. So the derivative of x to the power of 2 times y plus the derivative of y cubed equals the derivative of 7. So for x to the power of 2 times y, we use the product rule. We get 2xy plus x squared dy dx. And then for y cubed, we use the chain rule. So then we get 3y squared dy dx. So now we have 2xy plus x squared dy dx plus 3y squared dy dx equals 0. And then we group the dy dx terms together. So once we do that, we get x squared dy dx plus 3y squared dy dx equals negative 2xy. We can factor dy dx out. Equals negative 2xy. And then we just divide whatever's in the parentheses. So now our final answer is just negative 2xy all over x squared plus 3y squared. That's a really common algebra pattern in implicit differentiation. So you collect all these derivative terms, like we did in the last problem. We factor the dy dx out, and then we just divide. Let's move on to the next question. So pause the video if you want to try this question out. Okay, so this one has a logarithm, so we'll need a chain rule again. So we're going to differentiate both sides. The derivative of ln u is 1 over u times the derivative of u. So we get 1 over x plus y times 1 plus dy dx equals x dy dx plus y. So now let's solve for dy dx. We first multiply both sides by x plus y. And we're going to get 1 plus dy dx equal to x plus y times x dy dx plus y. We're going to expand this right side here. So we're going to get x times x plus y times dy dx plus y x plus y. Now let's move the derivative terms together. So we're going to get dy dx minus x times x plus y dy dx equals y times x plus y minus 1. And then so we're just going to be left with y times x plus y minus 1 all over 1 minus x times x plus y. Okay, we got that down. And you could leave it like that, and that would be completely correct. All right, we can move on to the next problem. So we're going to find the derivative of x to the power 4 plus y to the power 4 equals 16. And again, pause the video to try this yourself. Give you guys a few seconds here. Okay, let's finish with one that looks familiar. So we're going to differentiate both sides. We're going to get 4x cubed plus 4y cubed dy dx equals 0. And then we're able to solve for dy dx. So we're going to subtract 4x cubed to both sides. We're going to get that. And we're going to divide by 4y to the power of 3. And the final answer, you're just going to get negative x cubed over y cubed. Very similar structure to the earlier power examples, just with the fourth power this time. So, the big idea with implicit differentiation is this. You do almost everything the same way you normally differentiate. You use the power rule, the product rule, the chain rule, logarithms, exponentials. But every time a y shows up on the same side as an x, you have to remember that y depends on x. That's why dy dx keeps appearing. So the general process is this. Differentiate both sides, attach dy dx wherever you differentiate a y term, then solve algebraically for dy dx. That's really what implicit differentiation is. Once you get more comfortable with that pattern, these problems become much more manageable. Thanks for watching, and I'll see you in the next one.